So this is the third look at this board now. Someone has sent me this power amplifier, and we have the differential input stage, we have some current mirror, current source, another current mirror, another differential stage which is doing amplifying, current sink here, something to spread the voltage of the gates of the two FETs so that we are in the class B, and then we've got the push-pull output stage, and we've got a little zonal network and some feedback arrangement here with an extra port 0, which is what C10 is doing with R19 and R18. And C9 is there to get rid of the gain at low frequencies, and we've got a passive input filter as well. These four rather, are decoupling. This is the power supply, and this is the output connector, that's input connector. We'll take a look at the board. Board looks pretty good really. There's not very much needs adjusting. Heatsink will go here on the top side, and the devices sit perpendicular to the board, and the heatsink is perpendicular to the board as well. This is power supply connector, that's output, that's input, I should have thought. Only a couple of things that are a little bit maybe need thinking about. First one is that a lot of the pads are still fairly small, and you really want to make the pads as big as you can get away with. So for the resistor I might, this is a Res 40, which is 40 thousandths between the pins. So you can do the calculation in metric if you want. This 40 over 1,000. No, not 0 divided by 40. Go away. 40 over 1,000 times 1. So that's 0.4 times 25.4. Rubbish. What did I do wrong there? You know what, I'll just measure it. It'll be much easier. Apparently it's 10.16 millimeters. It's 400 thousandths of an inch. That's why. An inch is 25.4 mil. So yeah, there we go. So that's about 10 mil. So I should maybe think about as big a pad as you can get away with. It's better to have the square pad if you can, because the pad is effectively glued to the board in the sense that the copper sheet is glued to the FR4, and then the FR4 is, the copper is covered in some photosensitive material, and then it's covered with a plastic sheet. And of course when you get it, if you're making your own circuit boards, you will expose the photosensitive material on top of the copper to whatever UV source you've got, having first interposed some partially transparent material which acts to cover up some of the photosensitive area. So in other words, it has the tracks and the pads and all the rest of it painted onto it, usually printed, in such a way that some of the photosensitive material is degraded by the UV and other parts are not, and then you develop it in a developer, and then you etch the board, and the bits which are undeveloped will not be affected by the etchant by virtue of them being protected by the photosensitive material which was not exposed, and what's left behind is just the tracks. And the bits that were exposed are the bits where the developer has developed the photosensitive material to the point where it's no longer effective because it's been had the UV exposed on it, and then of course the etchant removes the copper and leaves you with just the tracks. So in that sense, all the pads and all the tracks and everything else, the copper is glued to the board, because initially the copper is glued to the board when it's one whole sheet. When you've got little bits like the pads and you put the soldering iron on them, it effectively the heat unglues the pad a bit, and if you have to rework the board, maybe because there's a mistake or you need a design change, I don't know what, you will thermally cycle that little bit of glue. And it'll hot, cold, hot, cold, hot, cold, and eventually the glue gives up the ghost and the pad comes off on the end of the iron. And then you wipe it on the sponge, and then you swear because you can't solder to the pad anymore, and you have to have a little wire jumper to a bit of the track, and if there's a solder mask, you have to scrape away the solder mask with the scalpel so you can get to a little bit of copper that you can solder to. It's a big pain in the arse. So best thing you can do, have your iron as cold as you can get away with, but don't make a bad joint, and make the pads as big as you can. In order that there is more thermal mass there. Yes, you have to heat up that thermal mass, but it will survive a lot more thermal cycling. One thing you can do is actually take the resistor package, which is that one in this case, and you can decompose it, and you find out all its stuff and things. This, the type and stuff and things is here, so if you look at the 3D view, is it going to render anything else? Oh, there we go. Ooh, shiny. Those capacitors, the lighting on them is quite aggressive. There we go. The comedy stretch resistor is quite funny. This is this sort of thing. Much better off with the so that the bigger pad. The cylinder bit that it's talking about is to do with what it actually renders here. Nothing to do with anything useful. Well, that's useful to look at, but only tangentially. So we can put some big pads on, maybe. Oops, did I miss? Got to be careful you don't miss. Whoops, Control Z. I didn't miss, good. So then I can gather it all up, including all that stuff there, and make a package. And I can overwrite Res40, but it will save it in the user package. And it asks me if I want to modify all of the Res40 that are in this thing, and sure enough all the resistors have changed. It's very quick, very easy. The diodes I can do as well. I can also do the capacitors by the same method. I've introduced a design rule checker adjust here, where this trace is a little bit closer. I'm going to have to reroute that. What I might do is run it from here instead. It's by far the easiest way to get out of that. You might want to go around and do a few little housekeeping things like moving away the... Invariably I find that the silk is always a little bit conservative, in the sense that it's not quite big enough, and you end up covering up the labels a little bit. So you could try to make that and a little bit further away. This one here, when you have this manufactured, if you get it manufactured by a board house, they'll do what's, before they go into processing the board physically, somebody will sit down and run some tools, some software tools on your Gerber files, and one of the things they'll do is they'll clip the silk, and what will happen is around this region here, around where the pad is, perhaps not right around the edge of the ground plane where I've got the mouse now, but somewhere between the edge of the pad and the edge of the ground plane, something like that, they'll clip the silk, so this bit of the two would disappear. Now it might not matter if it's only that big, because it's still pretty obvious that it's a 2, but I could move it to there and that will print. So you want to do a little bit of that if you can. Q1, well, you won't see much of this Q1. What is more, I don't know if this is Q1 or is this Q1. I know now that this is Q1, so I'm just going to move that down there. I might move that one over there. I'll move it there. Could leave it there. We'll leave it there. Doesn't matter. This is okay. The traces will be under the solder mask. It's only exposed copper that the silk will get clipped from. There's a trace which isn't on the rat's nest. It shows it's not connected. In practice, it doesn't make any difference, but just because I like it to look nice. nice. We can maybe set the origin. So the origin down the bottom here has just gone purple because now I set that as the origin, and I can run it out like that. Now it's gone. It doesn't actually change it physically, but as far as the software is concerned, we changed it. So I just save that. What else is that should be done? Oh yeah, these transistor pads are pretty small. Not sure what transistor we're using here. What's Q1? Q1 is the 2N5401, very venerable transistor. I think I might even have suggested that in a previous video. Now I'm a bit worried. Total device dissipation, 625 milliwatts. We've got two supplies. I can't remember what the supplies are for this. They're probably about 25 volts, maybe 30 at a push. So it's 60 volts across the lot. That's not going to have too much go on, that's some. This will be at about 0, roughly speaking. This will be at about the rail, so we're probably going to have about, call it 25 across there. These will be pretty low, so call it 25 across there. What's the current? 0.7 for that, 0.7 for that, so 0.7 across 330. So that's 2.1 milliamps times 25 volts. 53 milliwatts for that Q3. And then it's half of that for each of Q1 and Q2, so that's alright. They should be okay. What about this one here? Oh, they're 340s. Fair enough. Yeah, you'll be alright. Good. Okay. Yeah, I reckon it'll be okay. Wouldn't want to advise you wrongly. That'd be bad. So I'm just going to make this a little bit bigger and see what I can get away with. Clearly you can't get away with that. There's no chance. That would be alright. It's a trade-off. If you put the pads too big, that gap is quite small. It's only I just press Control F1 then to give me the finest possible grid. 50 micron. You can change the grids in the grid snap in the technology menu, but we don't need to. So this gap here, I could, if I wanted to, just use these two numbers and deal with it that way, but I'll notice it's not quite on the grid. So this is roughly that's the board. You can zoom in until you can see the atoms. Of course, you can't actually do that in reality. So that's 250 microns, effectively. Near enough. That's substantially less than the width of a fingernail, I should have thought. And it's only, well, a human hair is 15 microns across. So that's you laid 10, 20 hairs next to each other. That's the territory you're in. It's a pretty small gap, in other words. You wouldn't want to do that. I don't think. I should go for the 60,000. It's hard for me to line it up now because the grid is so fine it doesn't want to snap properly. So I'm going to go back to a thick grid because then it will snap easily. So this gap is half a mil. Half a mil's believable, even with a world's not greatest soldering iron. Half a mil will do you proud. So that'd be alright. These ones, whatever you want, doesn't matter. Sometimes, especially if you've got ICs, you'll find that one of the pins has got a square pad and all the rest are round. If it's a through-hole device. If it's surface mount, well, they will all have the little surface mount pads. They'll all be rectangular, possibly square, but more often than not rectangular. you might decide you want to have the round pads. Then the chances are, in the case of a through-hole IC, usually, unless it's a very high-speed IC, you have a chip carrier. If you don't know what chip carrier is, I'll try and get one. Good old Wikipedia. You can have my £2 a month. I was rather hoping for a better picture. These are chip carriers, they're just not quite the one I wanted to see. That's a chip carrier. Both of these you could get from the EEE store. This one is actually a bit better than that one. These are sprung, and they're a bit more forgiving when you push the chip in if it's not dead right. If you get this one wrong, you'll just collapse a leg, and then you have to straighten it, and then it'll be weak, and so on and so forth. They're chip carriers, and the idea is if you blow the chip up, you can whip the chip out with a screwdriver and put a new one in. Now, you shouldn't blow the chip up, I agree, but the consequence of that is you are unlikely to have to rework those pins with an iron. Consequently, you need not fear a round pad because you're unlikely to have to do any rework. So you might want to do that in the case where you've got ICs. So I would probably do the transistors the same, and I would not do that individually. I would do it by decomposing the package. Same goes for here. If you can, try and make the middles bigger than you need to. The reason is, if you are getting the board made in a board house as opposed to making it yourself, you will get plated through holes, and if you get plated through holes, you'll find that the solder, if you ever need to get it out of the hole, is quite unwilling, because actually it's quite happy being in the hole, and there's a good deal of surface tension trying to keep it there. And if you look in Tektronix scopes from the 70s and 60s, the dog kennel style scopes, you'll find that scopes were really expensive back then because they were all analog, and it took an awful lot of non-recurring engineering costs were involved in their production. That's to say, a lot of design time. And of course they were handmade, more or less completely handmade. And you had to pay somebody, and if it was Tech or HP, you were probably paying an American, because China weren't making things, and neither was Japan in the very early days. So you've got quite high labour costs as well. So the scopes were expensive, and it was expected that people got them repaired rather than chucking them out, or recycling them, sorry. But I think we both know I mean chucking them out. Consequently, the people who were designing the scopes were designing the circuit boards with the intention that you would have a service contract, you being the owner, with the company who made them, and the technicians from that company would have the job of servicing this equipment, having to repair it. So it paid them, they saved money by making sure that it was easy for the technician to fix the board, because then they would do it quickly and they could get on to the next one, and of course they fulfill their service contract that way, swiftly. So they made the holes extra big in order that it was easy to get the solder out and get the new component in, and there's no reason why you shouldn't do the same. If you look in some of those scopes, you'll find a couple of millimetre holes sometimes, and you can do that by editing a pad. So let's say I make a new pad. Maybe I want it to be S. Let's call it S, I don't know, 80, and we have a 2.5 millimetre hole. We try it, and we'll make it square. So it's square. I don't know how big 80 thou is. It might be that 2.5 millimetres is impossible. I might have to go back, but we'll see. So it's a square of 80 thou. I could do the whole thing in millimetres if I want to. That might be very, very sensible. You can mix and match your units, no problem there. The guard gap, I will put 1/10 down. guard gap of a fifth a bit. You wouldn't really have it on a board that's got pads this sizes. The drill cannot be smaller than the pad. Okay, fair enough. That's clearly my fault. Let's do it all in mil then, because my brain prefers to work in millimeters. Let's make it in a 3.5 mil pad with a 2.5 mil drill hole, because I know that'll fit. The guard gap, I don't care, I always leave a tenth. So I've got a big pad now. You can see, look, I mean, I know I put it there, but I could if I wanted to. That's okay. That's okay. The wire will go through that hole very easily, with plenty of space to spare. And the solder will flow in the joint, and the resistor's not going to drop out, it's soldered in. I might have been a little bit mean with the pad, but you must balance this against the fact that you've got to run tracks and you can't have all your board taken up with pads. You could go for a 4 mil across on a board like this. Maybe the hole size is a bit excessive. Maybe we can go down to a 3 milli device with the damn. I've edited the name, not changed the fact. With a 2 milli hole. I'm just tabbing through the boxes in the usual way. Yeah, that looks a bit more feasible. I'm not sure it's lined up properly. Maybe the one is in not quite the right place. So I find the resistor's got quite a thin lead, and if you need to know the thickness of the lead on the resistor, you can go and look it up in the resistor's data sheet. When you're buying these terminal blocks, like this one, it's actually pretty serious. This hole, I think, is probably too small. The pad is fine, but the hole is too small. When you get the board made, the through hole will be plated, and if you have to drill out that hole a bit to make it bigger, you have to be careful not to destroy all the through hole plating. If you do, then you need connections on both sides, which you don't here. But suppose, for example, I was going to run off something like that, go somewhere else. Now I need to solder the top and bottom sides, and I can't solder the top side because on the top side, don't know if it's on the visualizer, it might be. Yeah, whoops, makes you feel sick. I can't get the solder. Oh, god damn. Oh, sorry, my driving. I can't get the soldering iron under this green block, which is supposed to be the terminal block, because it meets the board. It's not like this, the leg of this capacitor, where I could put a bit of solder there if I needed to. No chance. So if you solder it, it has to be on the bottom side. When you solder it, it has to be on the bottom side. And you need to have it plated if you're going to run things. Come on, there we go. Off the top, like that little wire, that little track there that I added. And in this case, it doesn't matter, but just suppose. So you want to make sure you've got the right. I could even make those a bit bigger for this particular circumstance. If I did make these bigger, would it make that one bigger as well? Would just make a silly change? Yes, it would. So that's better for this size, but that's too big for here. So you need to be careful you don't decide to do changes later and find that you've got problems. What else? That applies to that one and that one as well. Not much else really. The drill holes are fine. These are done, by the way. You get your pad, I don't know, call it that one for the sake of argument. The reason that up here I can only see the drill mark is if you look down here, I'm on the drill hole layer. So if I go to all, I'll get a usual pad. There's the pad. But if I put it to the drill layer, I will get just the hole. They are useful for, essentially you mark out where you're going to mount the board onto the enclosure or whatever. It's going to be if you're going to do it with a standoff post or something like that. You need to leave enough space around it to run a nut onto the thread, or if it's going to clip on, the clip must expand a bit, that sort of thing. The tracking is fine. There's no problem there. Can't see anything wrong other than that little bit with the pad sizing maybe. The size of the lettering is good, the thickness of the lettering is good. These are probably not too close together, even though they're right next to each other. I think it will be alright. You could move them a bit if you wanted, desperate. On the back, if we need to look at just the back, you can edit the layers, ask for nothing, get the bottom copper, the bottom silk, and the, I usually like to have the rats on, but there aren't any rats at the moment. And you can see, you're still looking through the front side of the board, so all the text is backwards, or mirrored rather. It just lets you see. So yeah, it looks okay. There's just a few little surface mount components. Here we've got this hole, and it's a copper plated hole, and that allows us to link the lower and upper ground planes together. So if I was looking, for example, here's the main ground for the board. So that's where the current returns to the ground from the upper supply, and it flows out of the ground into the lower supply via the transistors and so forth. The speaker current leaves and goes into the speaker from pin 1 of this terminal block, and it returns via pin 2, or if you prefer you can think of it as leaving via pin 2, going off to the speaker and returning via pin 1. Because it's AC, it will be half and half depending on where you are in the waveform. So it's easy for the currents to return from pin 2 to this pin 2. There's plenty of copper here, not much in the way really. We don't expect there to be a voltage drop between these two, because there's some copper, there will be a resistance or resistivity, and there is a thickness of the copper on the board, and so on and so forth. It could be a little voltage drop, and it's very undesirable. You want ground to be the same voltage all over your circuit board, because otherwise your circuit will not work the way you expect, and you get all sorts of funny transmission line effects start to take hold. So how easy is it for current from this decoupling cap? Because this decoupling cap has to see ground here in order to decouple this node to ground. Otherwise it's just decoupling this node to whatever this local voltage is on this ground plane. And if the ground plane doesn't have good access to the main ground point, voltages will develop. If you want a very high resistance pathway, you use a very, very thin wire. So did we accidentally make a thin wire? Well, current can't go down here. Well, it can, but it's not gonna, because there's nowhere for it to go. It can go through there, and it can go through there. And if it does, well, then it will go down there, through there, or through there, and then through there. These are both quite thin. It's quite a torturous route, really. I don't really want to move any of the components. I don't really want to relay any of the tracks, but I would like it if it was an easier route for C16's quote-unquote ground end to get back to pin 2. So what will I do? Well, I can, same applies for C15, although C15 is not as bad. There's one down here, but that's easy. This applies equally well to decoupling caps you've got on the top side. I don't see one at the moment, but oh, here's one. This is probably a decoupling cap, probably. How does that get back? Well, it's either going to go up here and round, or down there and round. Down there and round is a very unfavourable route, because this hole is, there's nothing there, it's barely. You can use the top ground plane to help you. Nope, sorry, not that one. There, you can do it from now. There it is. So if I add the top copper, take off the silks. So now what? I could even take off the bottom copper too. Make it really plain. How can this current get back to here? Well, it's dead easy. Straight across the top. There's nothing to stop this. Very, very little tracking on this surface. Consequently, it's easy for currents to find their way to where they need to get to. And that's why I want to put a plated hole here between the ground planes, so that they're connected to each other and they form a better ground than just the lower ground plane could on its own. So I would do that in a few more places. We turn on everything so we can see what it is that we're working with. You've got one there, but that doesn't matter. It's got a very good access in. Here, I would certainly consider putting a little. It doesn't have to be very big, so you don't want to do anything with it. That size is enough. Right click to just then. Edit its properties. Relief, solid. Yeah. Oh yeah, and you've got to set the net. Yes. Put it on the ground now. There we go. These don't appear on the schematic. They're not in this diagram anywhere. They're only on here. Just get rid of that. They're to do with the layout. And I might consider doing that. I already know what that one's got. It has anyway. Usually it's okay to have the default relief if the pin is not going to have very substantial currents flowing in it, and in this case it isn't, so that's okay. Interestingly, now I've relieved the pin, you can see the difference in the upper and lower ground planes. The lower ground planes in blue and the upper ground planes in red, and if I go edit them by getting the layer tool up, I can look at the upper one. You see its relief is relief, and the clearance is 10 thou, and the boundary is 20 thou. If I try and pull up the lower ground plane, if you need to select the other ground plane, there's a slightly different relief, so there's boundary, sorry, so I could pull them like that, but if you're stuck for it, what you can do, check the bottom layer, and then click that, and it only allows you to select things that are on the bottom. So now it's impossible for me to select the upper layer. So if you've got a, I don't know, 4-layer board or 8-layer board or something, and you've got buried videos and all God knows what, things that will cost you a lot of money to produce, it can get quite difficult. So you can turn off certain things so that you don't see them, and the other thing you can do is, if you need to see things but you don't want to be able to select them, you can choose which layer you're working in. Right, so let's just have a look at this one. And you can see I set here the boundary is 20 thou, the relief is 20 thou, and the clearance as well, which is why we can see there's this difference. So just to make the board look a bit nicer, I'm going to set them up the same. So I select the top layer, and we'll put that to T20, and put that to solid, and that to 20 thou. Now you can see there's the same. You can't see the blue under the red anymore, they're identical. And we've got a little bit more clearance around everything, just to stop you bridging with the solder. If you've got a good solder mask, you probably won't be able to make a bridge to the ground plane by accident, but if you've made the board yourself and there's no solder mask, it's a pretty easy thing to do. Right, so some of the pins slightly bigger pads, some of the pads with slightly bigger holes if necessary for the component. You need to put some extra holes where you need to reinforce your ground plane by linking them together. What else was there I was going to do? Oh yeah, there's an odd little bit of track here that I noticed earlier. Don't really know what that's up to. Bit strange, don't need that. And that's broadly it. I'd produce this now with those changes that I just suggested. You're going to put your name on it, I guess. That's more or less it. Minor detail, depends how you're going to mount your heatsink, but if your heatsink extends the full width of this board, then you won't be able to put a nut onto whatever goes in here, whatever thread you have here, which holds the board to the enclosure, because the heatsink will be on top of it, so you might want to move those slightly different position. If this was an RF board, we'd have these little ground plane connectors they'd be regularly spaced, and they'd be all around the components where the grounds. You'd have several around here, especially if we were going to get to low gigahertz territory. And you would have, say, one there, one there, one there, one there, one there, all the way across, unless there was something in the way, in which case you'd move it to the nearest convenient position. And you make sure that they're at least a tenth of a wavelength. So if you're running at 3 gigahertz, wavelength's a centimetre. So you have them pretty damn close together if you can. Right, I think that'll do for now. So I'd probably send this off to, well, don't know, should I give an advertisement for a particular company? Don't know. There are some good ones. Leicester Circuits, Wrekin Circuits, W-R-I-K, I think. It's a big hill near Birmingham anyway, you can Google it. PCB Train, good, especially if you want them to populate it as well, because they do certain components which are free issue. In other words, it costs them money to receive from you components. Well, for all of them, it costs them time to decide and set up the machine to pick and place them. So if it's just resistors, they give you resistors for free because it saves them money overall. So if you're going to have it populated as well, which is quite an expensive affair, you might consider them. PCB Train, and there's some ones that do it out in the Far East very, very cheaply, but you sometimes have to wait sort of 21 days to get your delivery on that. Ragworm, not bad, made in Britain. Anyway, that'll definitely do for now.